Good morning, everyone. I'm delighted to serve as also the technical program chair of the academia track. I'm a professor at Johns Hopkins University in electrical and computer engineering and computer science. So today, we are delighted to introduce our keynote speaker, Dr. Mandy Pant, who is a senior technologist at Intel. Mandy, with over 20 years of experience in the semiconductor industry, as well as product management, has been deeply involved in research areas and academia and industry. So she has been deeply involved in various academic community, especially as serving as the TPC chair of conferences such as ISCC, DAC, ICCAT, and ESLPET. Mandy has been given numerous invited talks and keynote talks at the various sessions, and I would like with that to introduce the Mandy. Test. You can use this one.
Is that working? All right. Yes. Good morning, everyone. How's everyone doing? Good? All right. Awesome. Thank you for the very kind introduction. All right. And my talk is going to be about emerging technologies, slightly different from what you guys are used to, but let's see how it goes. Let's say, as a little girl back in the 80s, and I think that will date me, I remember a vivid conversation with my dad. My dad himself was an electronics engineer. And then I remember him getting me all excited by telling me that the world's fastest computer had been built by Intel and ran at a whopping speed of 90 megahertz. Yes, the year was 1989, and the chip was Intel's 486 microprocessor. I remember him telling me that computers and computing is going to change the world. And that conversation was very pivotal in my own trajectory, and I began dreaming about being part of teams that are going to build technologies that will change the world. So now fast forward a few decades later, and it goes without saying that computing is an integral part of our lives. How many of you remember the defective CrowdStrike update that happened on Microsoft Windows? It sent all computers, literally all computers around the world on a reboot death spiral. It brought life as we know it to a grinding halt. It impacted airline systems, the hotel reservation systems, banking, hospitals. It's hard to imagine life without technology. And moving forward, this nexus is only going to get stronger. All right? So some of you, I'm assuming some of you may be familiar with an S-curve. Familiar with an S-curve? Okay, what I'm showing on the screen is a technology S-curve. It has an initial phase. It's called the infancy phase, where it's just starting off. Then it has an exponential phase, which is its growth phase, grows rapidly and quickly. And then it tapers off. It's a mature phase that tapers off. So the explosive growth that we have seen throughout the past few decades is essentially can be interpreted as a superposition or a stacking of individual technology S-curves, each with its own infancy phase, its own exponential growth phase, and then its own mature phase. And it is this superposition of different technologies that have been essentially fueling what we know as Moore's Law. How many of you are familiar with Moore's Law? I see a lot. How many of you believe it's dead or it's dying? There are a few who believe that. So let me tell you this. As long as we have emerging technologies, we will have Moore's Law continuing and be alive. So Moore's law effectively is a law of economics. And I did not make that up. This is essentially a clip of the paper that Gordon Moore has published. And you can see that highlighted over here, economics. It is a law of economics, which essentially states that the cost of a transistor will halve every 18 months to 2 years or so, right? And how have we been doing this? We have been essentially doing this so far by the shrinking of CMOS transistors. So Moore's law, effectively, it's not a law of nature. Essentially, it is an expectation of continued economic innovation. So as long as we have emerging technologies in the horizon, we will be continuing to realize Moore's law. So far, we have done it through the shrinking of transistors, but if you start as we move on ahead, and since the shrinking of transistors, that segment is getting harder and harder, we're moving and pivoting to other ways of continuing to push forth Moore's law forward. And right now, it's through heterogeneous 3D integration of chiplets, if you all have heard about chiplets, right, which are built on different process nodes that will push Moore's law, or is right now continuing to push forth Moore's law forward. Here are some examples of, let's see if I, okay. Yeah, these are some examples, and these are Intel examples here, but there are others, plenty of others, of chips which have come out containing chiplets, heterogeneous integration of chiplets. I've got listed here, there's Intel's Meteor Lake, there's an Agile FPGA, there's something called Ponte Vecchio, there's Intel Xeon Sapphire Rapids, and only yesterday I think we introduced the next generation, or launched the next generation of Xeon, which is Granite Rapids. There are details there on links, and if you guys want to learn more, you can always click on the links and learn more about it. But the point that I'm making is that chiplet design is becoming prevalent, and that today is what is essentially pushing Moore's law forward. Right? So let that sink in. Moore's law is not dead. And as long as we have emerging technologies in the horizon, Moore's law will continue to remain alive. All right? So while conceptually, AI has been around for a while. I remember when I was an undergrad, AI was in my textbook. I had studied AI. But it is only recently that AI has become a reality, and of course, fueling a revolution here, simply because we've managed, or we have finally got to enabling massively parallel computation, right? We've got to enable memories with significant amount of capacity and speed, and also high-speed I/O links. It's basically the hardware, the computer hardware progress, which has essentially now allowed us to make AI a reality. So I'm going to talk about a few emerging technologies that will help us understand why we have promise for the future, and perhaps why you guys should be interested in knowing about it. And these technologies essentially advance very basic metrics. Metrics of size, of speed, of accuracy, of capacity, of efficiency, which is, again, of deep interest to this audience. Here, of security, of reliability, of determinism. Again, these are all characteristics or properties that are absolutely required as we move to deploying AI at scale applications. Whether you talk about precision medicine, whether you talk about personalized education, these are all examples of a world that we want to be in. And this is essentially required. There are basic characteristics that need to be realized to help us get there. All right, so let me, any of you familiar with nanoelectronics, the field of nanoelectronics? Right? So let's look at the emerging field of nanoelectronics. So what is nanoelectronics? Essentially deals with the design and fabrication and the application of devices and circuits at a very, very tiny scale. It's called the nanometer scale, the size of atoms and molecules. Examples, nanotubes, nanowires, nanoribbons, nanodots, graphene, quantum dots, etc. These are some examples of it. But here's the thing. Nanoelectronics essentially allows these materials to have very, very unique properties due to their tiny size. Right? Properties such as molecular recognition, properties such as self-assembly, properties such as quantum effects. Now, there are these materials which have properties like molecular recognition, they are very useful in precision medicine because you can do targeted treatments, you can do precise diagnosis, they help with accelerated drug discovery, drug delivery, etc. Now, again, nanomaterials with properties, demonstrating properties of self-assembly, they are used essentially in developing sustainable plastics. They are used in surgical instruments. They're used for, again, accelerated drug delivery, etc. Now, nanoelectronics demonstrating properties of quantum effects. They have enabled a completely new class of computing called quantum computing. So, and quantum computing is one of the few emerging technologies on that S-curve, on the set of S-curves that continue to forward, Moore's law moving forward. So let me talk a little bit about quantum computing. Right? The basic source of information, the basic unit of information in quantum computing is essentially a qubit. Right? Folks might be familiar with the basic unit of computing in classical computing, which is a bit. It's a binary digit. It can be a 0 or a 1. And today's computing language essentially is a string of zeros and ones. It's a string of bits. Right? Now, qubits, they have additional functions or properties over and are therefore different from the classical bits. In that, they can store a 0, they can store a 1, or they can be a superposition of a 0 or a 1. So the analogy of a qubit, it's analogous to a coin, which can be sitting on its head representing a 1, can be sitting on its tail representing a 0, or it could be spinning. If it's spinning, it's basically can be interpreted as a superposition of a 0 or a 1 in that it has some probability of falling on its head and becoming a 1, and some probability of falling on its tail and becoming a 0. So there is this property of superposition that it has. Now think about multiple spinning coins having a same probability of falling on its head and sharing the same probability of falling on its tail. This set of spinning coins essentially are said to be in a state of entanglement. So we have the properties of superposition and properties of entanglement. And as a result of this, if you have n qubits, each qubit with representing 2 states, if you have n qubits, you basically have 2 to the n states. So if you have 50 qubits, you have 2 to the 50 states, which is quite a significant number of bits. If you have 300 qubits, just 300 qubits, you have 2 to the 300 states, which is more than the atoms of molecules in the universe. So significant number of significant amount of increased information can be stored when you have qubits. Let me give you another analogy, just so that it becomes evident. Think of an artist painting in black and white. Artists can still paint, you have nice artwork coming out, but it is in black and white. Now think about giving the artist a full palette of different shades and different colors of crayons. And suddenly the artist is painting all kinds of details because of the multiple colors and different shades that the artist could not represent when painting with just black and white. So black and white, the analogy is the regular bits that we have today. And the moment you give the artist a full palette of different crayons and colors, the analogy is similar to having qubits, which give you the flexibility and power, and that opens up opportunities for applications that were hitherto not possible because of two things. One is you can store a large amount of information, therefore you can solve complex problems. And second, because of the properties of entanglement, you can essentially do a lot more parallelism. A lot of the operations can be done in parallel. So there is a speed, because it can be done very quickly, and you can store a lot more information in there. So we have quantum computing applications are essentially growing. You have cryptography, advanced drug delivery, financial modeling, weather prediction, traffic optimizations, etc., are some of the examples where you will see quantum computing essentially enabling what we've so far been dreaming about, right? Another emerging technology, and I know Pete mentioned this, and some of you might already be actively looking at this, is essentially neuromorphic computing. And neuromorphic computing essentially is computing that is inspired by the human brain. Now, human brain, any idea on how much power is consumed by the human brain? Any numbers? 20 watts, 20 watts. And let me tell you, if you're talking about taking a data center chip, a single chip, I'm not talking of an entire data center, you're looking at starting 400, 500 watts. Higher GPU chips are even higher. Brain consumes a mere 20 watts of power on an average. How can that not be inspiring? So neuromorphic computing essentially is inspired by the human brain, and it's looking to overcome the shortfalls of latency and speed and slowness that today's classical computing, digital computers have. It is still in its infancy. There are a few world applications, but in general, mostly it is in the research phase, whether it is in academia or with the government or in the industries out there. But applications are definitely in the edge computing space, in the robotics space, and autonomous driving, autonomous vehicles. Neuromorphic computing has demonstrated a lot of promise. So what I have here, and this is just a preview, I just thought I would flash up over here examples of hardware that is being essentially built by Intel as we push forward the frontier of quantum computing and neuromorphic computing. The one on your left is by Sandia National Labs. It's a Hala Point. It's a neuromorphic computer, and it has inside of it Intel's Loihi chips. And that it essentially enables AI inferencing and optimization about 100x less energy, and it speeds up to 50x faster than conventional CPU and GPU architectures. And then on your right is essentially, it's a silicon-based qubit wafer. It's a 300 millimeter wafer that's being manufactured here. And as we essentially take the next step towards building silicon-based quantum computers, we're getting there. So quantum computing and neuromorphic computing technologies essentially are spawning. They're spawning the next generation of S-curves. They're at the infancy, but the next generation of S-curves. And they will essentially continue to keep alive relentlessly Moore's law, and there's also Bell's law of computing, which is essentially a new class of computing every 10 years, right? So the explosive growth of computing technology that we are witnessing here is well poised to continue into the future. And talking about quantum computing or neuromorphic computing, etc., they essentially offer opportunities that will help us rapidly push forth this whole entire wave of AI that is riding upon us. So these emerging technologies, effectively, they will allow us to participate in a future that we would like to witness. A future that would augment our intelligence and enrich the lives of all of us on the planet. Thank you very much.